Everyone, this is Mr. Lee. In this video, I'm going to go over the energy in a closed system. This is also called the conservation of energy or the law of conservation of energy. And probably in this year, this video alone or this topic alone, I would put it as either like number one or number two. Definitely number one in terms of importance for humanity and also in terms of importance for this class and the AP exam. This is definitely up there. The conservation of energy is very important. It helps us. I don't know, it's a law that governs the universe. It helped us discover things like dark energy and dark matter. Um, and it helps us like look into and theorize about the beginning of the universe, the beginning of our solar system, the beginning of life that we know here on Earth. It's a pretty crazy topic, but we're not here to go into the crazy part of it. I'm here to introduce to you the basics of conservation of energy. All right. So the first thing I want to go over is the two types of energy that we have discovered so far, both in the kinetic energy lab. The first type of energy is the kinetic energy, and you'll see me write that as KE. KE is equal to 1/2 mv squared. So the important thing about this, okay, put a little star there, is the energy of motion. Okay, so whenever something is moving, we say that it has kinetic energy, and we know that it's the energy of motion because if we take a look at the formula, right, we have that V, right, and throughout the lab, we saw why that V is squared, because the proportionality between your starting energy and how fast the object went was a square proportion. And we know we're talking about objects because the variable for objects is that m right there. Okay, so this is the energy of motion. So if anything is moving, it must have kinetic energy. All right. The second formula that we discuss in the post-lab video is the formula I actually gave you, but I didn't call it this when I introduced this lab to you. It's called potential energy. So U subscript G is called MGH. All right, so put a little star there. This is the potential energy. Huh. And the U stands for potential, and that subscript G shows us that we are looking at, put this in parentheses, gravitational potential. Gravitational potential. All right, and we know we're talking about gravitational potential energy because there's going to be a G that's involved. When we do different kinds of gravitation or different kinds of potential energy, there's going to be a different variable that tells you what type of energy we're messing with. So the idea of gravitational potential energy, basically conceptually, is that it is height dependent. Okay. So what that means is that if a object is at a height that is not at zero, so if m is not at 0 meters, then it has potential energy. Now, the term potential energy actually links to another variable called work, but that's for a different video and it's for later on. But the big idea here is that the potential energy, for us at least, it turns into kinetic energy. Now, later on, when we get more advanced, we'll see how it does different things. But for those of you that are interested about the actualities and the nuances of physics, this idea of energy and this idea of potential energy, it gets pretty crazy. So I'm going to do a quick little side note. So a lot of the times in textbooks, you'll see this being called stored energy. So the energy is stored, and when the energy is stored, it has the quote unquote potential to turn to different forms of energy. But I don't like calling it stored energy because there's a huge misnomer, which means that within the name, it's a mistake. So if I were to ask you, where's the energy stored, right? Where is the energy stored? A lot of the times people will say, well, the energy is stored in the object, right? So if an object, let's say we have a table, and we have let's say that's the floor, and we have a red box on top of the table, right? And because, let's just break this down, this object, right, has a mass of m, it's at a height of h, and we're here on Earth, that we can call that g, right? And it's not moving, and so yes, we have an object, but it's not moving. It doesn't have kinetic energy. If I were to ask you where's the energy stored, a lot of people will incorrectly say the object or the energy is stored in the object, but that's not even true. Right? So that's so untrue. I don't even want to write it. The true physics behind this is that the energy is stored in the gravitational field. And at this point, if you're scratching your head and you're thinking, what the heck is that? What does all this mean? What is a gravitational field? I thought it was just gravity. Is this why Mr. Lee keeps on yelling at me when I just say the word gravity? Well, the answer to that is yes. But the idea that the energy is stored in a gravitational field is important because the energy is not stored in the object, right? So that's the important idea here. So let's write that down. I'm gonna write this down in red because red means stop. This is an alert. Energy is not stored in the object. And you'll see this when we deal with another type of potential energy called spring potential energy. Okay, energy is not stored in the object. Very important. And so for UG, it's stored in the gravitational field. Okay, now the idea behind this gravitational field, I'll use an analogy later on when we actually get to the conservation of energy. Okay, so this is just a preliminary, right? We're just going over the basic definitions. Kinetic energy is the energy of motion, right? So if an object is moving, we have kinetic energy. If an object is not a height of 0, we say that it has potential energy, and it is height dependent. But at this moment, I need to come up with the definition or the law of conservation of energy. This is so important. I'm typing it out so that my messy handwriting does not distract you. It says the energy for the system cannot be created or destroyed. All right, so this is the very basic definition. You probably heard this throughout your entire science careers, but for us, the important idea here is that the energy initial, I'm going to put it here, mechanical, okay? So mechanical energy is the type of energy that we're talking about in this class. So kinetic energy, so let's see that, kinetic energy and potential energy is always equal to energy final, okay? So let's do a little space there. Okay, so and this is always going to be mechanical. All right, Ke and U. Now, there's a huge caveat, and I won't write what that caveat is because that's for, once again, a different video. All right, so there is a way to change the energy of a system, but until we get to that point, until we cross that bridge, we're saying that this is the case. Okay, so the energy for a system cannot be created or destroyed, which means that the initial energy is always equal to the final energy. And so right here actually comes up with our formula. So we can write that the initial kinetic energy, so Ke initial plus Ug initial is equal to Ke final plus Ug final, right? And if I want to be even more specific, we can write this as 1/2 mv initial squared plus mgh initial is equal to 1/2 mv final squared plus mgh final. Okay, so this is going to be the formula that we're going to be using for a couple of days, okay, until we change it up again. All right, so let's do a quick little recap. All right. Kinetic energy is the energy of motion. Potential energy, gravitation, is the energy of different heights. So the best way to really go about this is to actually see a an example and really identify where the different parts of energy lie. And so here I want to introduce to you a different kind of model. So when I talk about models here, this is a math model. Okay. The next thing I want to show you is a graphical model. So these are what we call the energy bar charts. Well, before we do that, let's actually take a look at a scenario. All right, so let's do a scenario of, you know what? Uh, we'll do a scenario of the table again. Okay, so here we have a table. And what's on the table? Well, in physics, most of the things that are on the table is a ball. All right, so we have a ball here on the table. Okay, and we're going to look at three different scenarios. This is scenario one. Okay, and scenario two, for whatever reason, we don't know what that reason is. The ball is falling off the table from rest. Okay, it says midway, pew, right? And so here we got to say that our initial velocity is 0. Here we are falling, so we do have a velocity and 3. We have the ball, and it is right about to hit the floor. Okay, so it is definitely moving. I'm going to draw my velocity, speed. It's going fast. That's why the lines are bigger. Okay, so like this. So we can call this V1, and we can call this V2, and we can call this V3. So a couple of important things. Here, the initial height, we'll call that H. Here, we'll call this halfway, right? So it's like halfway between the tabletop and the floor. So if you're wondering, what are you talking about, Mr. Lee? So this is my initial height H. Here, this is half of that height. And here we can say our height is 0. Now, our velocity here, we'll call it just V3. In the future, we'll just think of this as VF, meaning that it is still moving, right? It's like hitting the floor, but it's still moving, right? So in the previous units for kinematics, we discussed that as an object falls and is about to hit the floor, it is still considered to be moving. So after it hits the floor and after it stays on the floor for a long time, that's when it's at rest. But if it's like hitting the floor, it's still considered to be moving. All right, so here we have a graphical model. All right, so more models here. Now, I highly suggest that you always sketch it out, right? So sketching out the situation is so very important. And what you can do from here is with this graphical model, you can identify the different types of energy. So I'm going to do the two types of energy. So we have kinetic energy and we have gravitational potential. Okay, we have kinetic energy and we have gravitational potential. Here we have kinetic energy, and here we have gravitational potential. All right, so here we have the two types of energy for three different scenarios. And just as a reminder, right next to kinetic energy, I'm going to say that this is velocity dependent and this is height dependent. Okay, so this is velocity dependent, this is height dependent, this is velocity dependent, and this is height dependent. Now, when you first start off, like if this helps you out, I highly suggest that you go with this method first before you do the mathematical model. But I do highly suggest that you always sketch it out. So in the beginning, we said the object starts off from rest. So we do not have kinetic energy. But because it is at a height above the floor, we say it does have gravitational potential. All right. Second one. It is moving, right? Because it's falling. So we say, yes, it does have kinetic energy. And because it is a height above the ground, we say it does have gravitational potential. And for this one, okay, it is most definitely moving. It's moving the fastest it's ever moved. But because it is a height of 0, we say it has no gravitational potential energy. Now, here we can actually come up with a different kind of model. Okay, before we actually get to the mathematical model, because I know you all can do the math, but I want to show you all the different ways that you can use to solve this, and we'll be practicing all three of these methods. This is called the bar chart or the graphical model. Okay. Now, this is I've been seeing more and more of these types of questions on the AP exam. So this one is definitely worth your time. So the bar chart or the graphical model or the energy bar chart model. Okay. Sometimes you'll see me write it as the like this, the LOL model, right? But that's not like laughing out loud. It's just what the graph looks like before you start. So here, okay, so this is going to be scenario 1, this is going to be scenario 2, and you know what, let's add one more scenario. We'll call that scenario 3 over there. All right, so on the y-axis, we call this energy, right? Energy, okay. And in the x-axis, we just write the types of energy. So I'm going to keep it nice and simple. I'm going to write it K, I'm going to write it as U, okay? K and U. K and U. And the very last thing that I want you to add is called total energy. Let's just write it as TE. 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 Now, it's a good habit for us to write that TE, mainly because as we get progressively into this unit, our total energy will change, right? The conservation of energy, the law of conservation of energy, we add tiny little caveats to make it slightly different. All right, so taking a look at a graphical model, we say that our initial potential energy, okay, we start off with, let's do it nice and thick right there, all right? We only had potential energy, okay? And so our total energy is equal to our potential energy. Let's do this in green. Yeah. All right. Okay. And so if you're wondering right here in the middle, what does the middle represent? Well, the middle is what we call the system. Now, we dealt with the system before when we did the force body diagrams. Remember how we used to do dotted lines around the Atwood machines? So now it's back, right? So if you're wondering why we drew a circle around it, well, because here it goes, right? Here's the circle for the system. So the system for us here, we only had the ball and we had the Earth. So the important part about this system idea, okay, and why the system in the middle is so important is you have to think to yourself, well, is there anything else that's interacting with the system, okay, other than the ball and the Earth? And the question is, or the answer is no. But if the question was yes, that would actually change how you approach the problem entirely. But luckily for us, once again, future video, there's nothing else that's interacting with the system. And so, we're good, we're safe. And so if there's nothing else interacting with the system, okay, I want you to write down that your TE initial equals TE final, right? So this is very important. And this is one of those things, the more you do this, okay, and if you do this over and over and over again, when it comes time for FEQs or FRQs, it's one of those things where because you do it so much, it just becomes muscle memory. And it's one of those things, if you write it down, it's like almost a guaranteed point. All right, so scenario 2, we have half of the height. So because potential energy is height dependent, we can say that we have half the potential energy. Okay, and so according to the law of conservation of energy, the energy you start off with is the energy that you end with, and we just wrote that your TE initial and your TE final have to be the same. So if half of our energy, or half of our gravitational potential energy, went to something else, we say, well, what did it turn into? The answer is it went into kinetic energy. So half of that went to kinetic energy. But here's the important part. This is the most important part because this is the conservation of energy. We say that our total energy doesn't change, like so. All right, so now we're going from scenario 2 to 3. Once again, let's write down our system. Our system is the ball, and it's the Earth. Just do a quick little check. Between halfway to the floor and actually hitting the floor, was there anything else that interacted with the ball? And the answer is no, nothing else interacted with the ball. So we can say that TE initial is equal to TE final, like so. Okay, so that's a good little check for you to do. According to up here, we only have we only have kinetic energy. And so I'm going to make this the biggest part of my bar chart. Okay, according to our model up here, we have no potential energy, so I'm going to leave that one blank. But because we had this little statement down here, we can say that our initial energy and our final energy, that does not itself change. So we're going to leave that like so. All right, so the third column is mainly there to make sure that you're not breaking any laws, right? We're not breaking the laws of conservation of energy. And so this is the graphical model. It goes back to what we did up here with the drawing to make sure we can see, how the energy is going from one form to the other. So we can see here, initially, it started off all as initial or potential energy. As it's moving, some of that potential energy turns into kinetic energy, but at the very end, all that initial potential energy turns into the kinetic energy at the end. So you're wondering, okay, so that's fine and all. I can draw colors, I can draw bar charts, but what about the formula? Okay, how does the formula come into play? So this is the formula that I gave you, right, to start off with. But we can actually expand this a little bit more so that it goes into these three systems. So the formula I gave you before was just when we're looking at two different parts of an object's motion, the initial and the final. But what I wanted to show you was a three-part problem where we're looking at the initial, the middle, and the very, very end. And so the formula itself actually doesn't change. We can say the mechanical energy initial, and just as a reminder, mechanical energy is potential energy and kinetic energy, okay? Or mechanical energy 1 will equal to mechanical energy 2, which will equal to mechanical energy 3. Now, here's the cool part. Based on the problem, right, if we're looking for a variable, let's say how fast is it going halfway through, okay, we only have to focus on the initial and mechanical energy 2. So let's write that down. If problem asks how fast at half point, okay, we just have to write the initial equals to the halfway point. But let's say if problem asks how fast does it land, we don't even care about the middle part. We just care about the initial part and the final part, right? ME1 is equal to ME3. So that's why this idea here is so powerful. Based on what the problem is asking, okay, we can look at the specific parts. But what I want you to notice is that we always start off with the initial, right? ME1 is always going to be your very first part of the formula. And based on different parts of the formula, you can look at either ME2 or ME3 or ME4, 5, 6, 7, 8, whatever the problem asks you to look at. And so for this situation here, just so that we have everything there, we can say gravitational potential initial plus kinetic energy initial. I should be writing once instead, excuse me. Gravitational potential energy 2 plus kinetic energy 2 is equal to gravitational potential energy 3 plus kinetic energy 3. Now, there wasn't a problem that was, linked to this problem, and that's something that we'll work on in class. But if we go back to this graphical model, we can see how this formula cleans up, right? We can see that initially we don't have any kinetic energy, and at the end we don't have any final energy. And so if we were to analyze the problem before, the formula just cleans up so that it looks like this. Like so, okay? Because our initial kinetic energy and a gravitational potential energy at the bottom does not exist. And here's the cool part, right? So we can see here, this formula right there links up to what we drew up here. Initially, we only have potential energy. In the middle, we have both kinds of energy. And at the end, we only have kinetic energy, okay? But the important thing is that the energy throughout the system, it does not change. And based on what the problem is asking for, you can look at specific parts, right? You can look at either ME2 or ME3, but you always have to start off with your initial potential energy, or ME1. All right, Now, at this point, I want you to hopefully realize that um, this is what we've been working on since the beginning of the year. This is kinematics, where the objects were being dropped, but it is a more powerful tool than kinematics. And the power from this is that it approaches physics through a different lens, a different model. This is the energy model, whereas before we were looking at the model of a moving object or a motion of an object, but this is the energy model. Okay, so basically the same thing that we did at the beginning of the year, but now we're able to apply a different set of formulas to analyze the same thing, right? An object that is moving. All right, so that's that. We will get a lot more practice in class. I'll see you later. Bye bye.